right, so we're going to be talking calculus today. We're going to look at the diagnostic tests. So we're going to start looking at some algebra here. So we want to know things like exponents, so rules of exponents, things like raising things to powers, and how that affects negative signs, raising it to negative exponents, dividing exponential expressions, raising exponential quotients to powers, and also raising numbers to fractions, and what that all means. So you should know those. We also need to know how to multiply complex expressions and how to do arithmetic with radicals and a mix of all of them. We also want to know about distributive property and how to distribute numbers out to expressions. We should know how to multiply binomials and how to multiply by their conjugate, and what that means and how and when to use. We also want to know how to multiply binomials or raise them to exponents, which just results in multiplication again. Factoring, you should know some good tricks to factor these guys. Simplifying rational expressions, right? Turn them into factored form and cross out any like terms, just like with numbers. You need to know how to multiply rational expressions, right? Numerator times numerator, denominator times denominator, and simplify anything that's needed. How to subtract fractions in fractions, and how that ends usually. And you want to know addition, subtraction with rational expressions, just like with fractions. Okay. So we can treat rational expressions just like fractions, and we can also treat fractions within fractions just like fractions. All right. You should know what it means to rationalize things and how to simplify things. Complete the square. How to solve general equations such as quadratics, quartics, rationals, absolute values, exponentials. You should know how to solve inequalities and when to change the sign of an inequality. Multiplying or dividing by -1 will force that to happen. You should know some good algebra identities. This is definitely false, right? Raising a binomial to the power of 2 is not the same as squaring each term. It's the same as multiplying a binomial by itself, which has its own unique multiplication. Okay. You should know general radicals. This is true. If I have the square root of a times b, that's the same as the square root of a times the square root of b. You can chop them up like that. It's multiplicative. The radical symbol is multiplicative, which is what this means. Okay, another one. This is false. Taking the square root of a squared plus b squared is not a plus b. Again, you can't just, like a, you can't just distribute exponents onto each term because it's a binomial, which is different from being a number or just a nomial. Okay, let's see. Is D true? D is not true because 1 plus TC over C would be equal to 1 over C plus TC over C. So the T term is correct here, but not the 1 term. It should be 1 over C. That will make this true. Okay, another mistake here. You can't break up the denominator like you can break up the numerator for fractions. In other words, if this was x minus y on the top and then over 1, it would be x minus y. So but this is not equivalent. Last but not least, this is true. 1 over x over a divided by x minus b over x is equal to 1 over a minus b. And why is that true? So let's look here. So there's some algebra that's canceling out here. 1 over x over a over x minus b over x. Okay, so you can see they all have an x term, and you want to kind of basically factor it out. So I'm going to factor out like 1 over x, right? If I divide 1 over x by 1 over x, well, it's actually just, you end up with 1. And you divide anything by 1, it's 1, right? So I have 1 over x times 1 over, and then I could take out the 1 over x here, like so. All right, if I multiply this out, 1 over x, that doesn't look like a 1 over x. Let me fix that. 1 over x. So if I multiply this back out, I have a over x minus b over x, which is exactly on the left side. Okay, so if you have something over something, you can just cancel them out. Okay, and you're left with 1 over a minus b, which is exactly what it's equal to. All right. Okay, that goes without saying that if we studied this, this is just algebraically correct, but if we decided to study the domain and treat this as a function, then we're going to have some problems here. We can't just cancel out things like this because it will change the dynamic of the domain and the range. So, but in terms of algebra, this is totally fine. Okay. Okay, so you should know some analytic geometry, basic Euclidean geometry, how to find the equation of lines, what to interpret, what type of information to extract from equations of lines, such as the slope, when two lines are parallel, when two lines are perpendicular, things like this. Okay, what else should you know? You should know how to algebraically determine basic geometry shapes, such as a circle, as you can see. So we start with a line, next step is a circle. You should know what the equation is for a circle. It's going to be a degree 2 polynomial, multivariable polynomial. X squared plus y squared minus 6x plus 10y plus 9 is a perfectly good circle. You need to be able to find the equation here. Notice this is not in standard form. This is in, I don't know what this form, I can't remember what this form is named, but you can turn this so that you combine your x terms and you combine your y terms such that you can see what the center is. So you would see what the center is in the form of x minus h squared plus y minus k squared equals r. In this case, the center here would be hk. Oops. HK, but as you can see, we don't have that term, or sorry, that equation in that form. And so what you would need to do is get the x terms together, as I'm doing now. It's 10y equals, and I'm going to subtract 9 to the other side, because as you can see, we have equal to r. Ooh, this is r squared, sorry. Okay, so what you need to do here is you're going to need to do completing the square. So essentially, you do x squared minus 6x. You take your b term, divide it by 2, which is negative 6 over 2, which is negative 3. Square that, plus 9. Go to the next one. We have y squared plus 10y. Half of 10 is 5. Square that is 25. Okay. So on this side, I've added 9. I've also added 25. So if I add 9 to negative 9, so I got to do that to the right side as well. So negative 9 plus 25. Well, it's going to be 25 because negative 9 plus 9 is 0. I'm still left with 25. So I add 25 on the left side. Now you combine your terms because you can complete the square here, meaning you can write the quadratic as a squared binomial. So we have x minus 3 squared plus y plus 5 squared equals 25. So the center of this guy, of this circle, is going to be at 3, negative 5, and it's going to have a radius of 5. Okay, very cool. Next, you should be able to sketch inequalities. Okay, fairly self-explanatory, I believe, and not super necessary in the beginning of calculus, so let's not worry about it too much. But essentially, if you're looking at something like x is greater than or equal to 1, what does that look like? Well, it says consider the x terms that are greater than or equal to 1. And if we were going to shade that region in the xy plane, well, that would look something like this. Say this is x equals 1, then it's going to look like this, right? All the values that are greater than 1 for the x-axis. So any point in this region is going to have an x value that's greater than or equal to 1, which is exactly what we want to show. All right, let's see. All right, next up is our functions. The graph of a function is given on the left. State the value, so you should know how to evaluate functions. You should know how to find the y coordinate or the x coordinate given the y coordinate. So if f of x equals 2, you should be able to find what x is by looking at the graph where the function is equal to 2, right? F of x is the function. You should be able to state domain and range, of course. You should know the difference quotient. What else do we have here? How to find domain of rational functions given if it has radicals or things in the denominator that could equal to 0, so you have to keep in mind of that. Okay, let's see. You should be able to sketch graphs by hand, something like x cubed, square root of x plus 1 to the power of 3. You have to basically think about the parent function or the basic function of the function that's given and sort of understand how to transform it based off of that. Yeah. All right. Cool. Functions. A lot of stuff for functions. I think we're starting with chapter 1 with functions. You should know some trig. Let's see. Yeah, you should just know trig in general, like converting to radians given degrees and vice versa. So there's just a formula for that, or you can sort of understand it geometrically, however you want. Find the length of an arc with a circle radius 12. So you should know these are just formulas that you should remember, or if you can't remember, then it's probably going to be in this book somewhere. So we don't have to worry about that too much. Find the exact values of trig functions given radians. Right? Again, this is like, you can convert pi over 3 to degrees if it's easier that way, or just know what pi over 3 is. So let's see. You should know how to find missing angles and missing sides of a triangle, of a right triangle, using trigonometry. Okay, you have some trig identities. These are kind of complex. I think you'll see these way later in calculus, so don't worry about it too much. And I think we're looking good. All right. So calculus was used over, let's see, for a very long time. So let's read this little blurb here. Calculus is fundamentally different from the mathematics that you have studied previously. Calculus is less static and more dynamic. Okay, it is concerned with change and motion. It deals with quantities that approach other quantities. For that reason, it may be useful to have an overview of that subject before beginning its intensive study. Here we give a glimpse to some of the main ideas of calculus by showing how the concept of the limit arises when we attempt to solve a variety of problems. So that's really what's separating calculus from most math classes you've taken up possibly up to this point. So things like the area problem, right? A long time ago, the ancient Greeks were trying to find the area of a circle. So, or sorry, they weren't finding the area of a circle. They were trying to find the value of pi. And to do that, they needed to find the circumference of the circle, which was difficult, right? Because the circumference of a circle deals with pi. So if you could find the circumference, then you can find pi very easily by using that formula that we all know. Circumference equals pi times diameter. So it's a ratio. So what we did was, in the past, the Greek, does it say who the Greek mathematician was? It was Archimedes, probably. I can't remember at the top of my head. So what he did was he drew polygons, regular polygons, meaning all equal sides. So here's a square, right? All equal sides. Here's an equilateral triangle. These are regular polygons. And what he did was he looked at a series of its series of polygons starting with the side numbers equal to 3, or equal to the subscript of a, right? So a sub 3 is going to be a 3-sided polygon, regular polygon, which is an equilateral triangle. Set s equal to 4, so a sub s. Again, we have a square, pentagon, hexagon, septagon. Okay, and then a sub 12, etc., etc. So what do we notice, right? Like if you look at a sub 12, this is a little further along in the series. Well, as you can see, the shape is still slightly there, but it's getting closer and closer when you look back to the circle, right? So starting here is the least amount of the circle, becomes more of a circle, becomes more. And so as that subscript starts running to infinity, that's exactly what it's gonna approach clearly. Okay. Okay. So that's an aspect of calculus that we're going to understand, which is called the limit. Right. We have this idea of tangent. This is going to be what's known as the derivative, right? We want to be able to find the slope of curves rather than just the slope of a line, right? We're actually extending the concept of a line, understanding its slope, and using that to find the slope of curves at particular points at point P. Okay, and that combines exactly what the area problem was doing, limits. You take a point over here and you take the point that you want to get to, you start dragging this down here to where the limit is, the limit as this approaches P. And that's what the slope is. Okay, has some uses in science, such as velocity. Not going to go too much into that. We can talk about that when we get there. The limit of a sequence. So, okay, newsflash or spoiler alert, not all sequences have a limit, so we'll understand when things have limits and how to prove when those are true. And that'll be useful for understanding if functions have a limiting factor, for instance, right? We can think of a function as a sequence of values or points. And yeah, so we'll get into that. All right, sum of a series. So if a sum of a series is convergent, that means I can add numbers infinitely and it's going to equal to something. Okay, so we look here. If you did, we can write 1 as 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc. plus 1 over the power of 2. So powers of reciprocals of 2 is going to equal to 1. So it has a limiting factor, which is just 1. And the only way to write this sum is infinitely. So it's like it's a way to find sums of an infinite number of fractions that equal 1, because we understand this idea of limiting of a limit and where that sequence ends up. In other words, well, a weird way to also understand this concept is 1 over 2 to the n is that exponent. If I raise 1/2 enough powers, eventually, actually never, it'll never hit 0, but it's going to approach 0 infinitely. It's going to keep getting smaller and smaller and smaller, and that distance becomes infinitely small. Okay, so that's an example of a really powerful idea in calculus, which is sum of series and convergence. All right. Okay, so yeah, chapter 1 on functions and limits. So the fundamental objects that we deal with in calculus are functions, okay? That's an interesting statement right off the bat. So we have to understand objects. We're going to think of functions as objects, as things that we can play with, right? You can play with an object. You can like play it with like a toy. You can also manipulate it, meaning you can, let's say you have a number and you multiply by -1. You're manipulating that number. So we could do the same thing to functions like we can do to numbers by manipulating them. Certain arithmetic follow as we change them. And like we want to know how to do that. Let's see. We stress that a function can be represented in different ways: by an equation, in a table, by a graph, or in words. Okay. So functions have they're not just one particular thing, but we can have different ways of expressing them. Okay. Let's see. We also talk about what a limit is, which is really good, super useful. Right. It's what the whole idea of calculus is. Okay. So you should know functions. I'm not going to go through too much of this stuff. Very elementary. You should just know like what a function is, how to find the domain, how to find the range, and you should know that a function is like a relation. Well, it isn't. It's a specific type of a relation, such that every element inside the set X in the domain has exactly one element, f of X, in a set E called the range. Okay. Okay. You should also know how to prove graphically when a function is a function, and that's using the vertical line test. Well, if the vertical line test fails, that means that there are 2 points on a vertical line, meaning that is not a function because you can't have one input with 2 different outputs. Okay. We have piecewise functions. Absolute value, very cool. Step functions, increasing and decreasing. Should know these terms. I'm going to skip on ahead. Okay, you have polynomials, you have power functions. So you should know a lot of these different functions and how to use them. You should already see these. I've seen these many times, so I'm not going to go over them. Exponential functions, how to transform them. How to describe a transformation. So you have vertical and horizontal shifts, stretching and reflecting. Composition. In higher level algebra, you understand that composition can also be thought of as multiplication. Pretty interesting, but that's a different time. Okay, so some tangent and velocity problems. So this is really going to be egging on the idea of slopes and how to find the derivative, which is the slope of a curve. Okay, limit of a function.